Hello 108 students, Mr. McHugh back with you on section 8.3. We're going to tackle page 2 here, and we're going to start simplifying radicals now. And we've got a couple guidelines we want to work with here on objective 3 here, so you want to take a look at those and see if you can feel comfortable with them. Turns out if you turn to page 445, they summarize them in a purple box here for you. I've got them here too. But so let's just take a look at these real fast. You've got ideas such as the radicand has no factor raised to a power greater than the index number. And what they're trying to say here is we're going to do one here down the road that if you had a raised to the third and you were going to take the square root of it, that is not simplified. Okay, and that's because you can break that down into a to the second square root times a to the first square root. And when you do that, now your clue was that the exponent is greater than the index number. So okay, you break it down. So what you do is you always go down to the next even number. So 2 plus 1 equals 3. Remember, when you multiply by the same base, add the exponent. So that's what you break it down to, and then you say, what's the square root of a squared? What times what gives you a squared? Answer is a. Square root of a, you leave alone. Okay, we're going to do that a couple more times. Okay, the radicand can have no fractions into it. Number 3, as we work on here, we're not going to see on this page, but there's no radical underneath can in the denominator. No radical in the denominator. They're saying something like if you had a result as 2 divided by the square root of 3, you would not leave it that way. Okay, we'll deal with that on the next page of the class notes here. Excuse me, how to handle that. Okay, so example rule 4, exponents in the radicand and index of the radical have no common factor. Okay, we'll see that coming down here. So what are we talking about here? Look at example 4, square root of 24. Now here's the hard part. You got to go back to old school before calculators. If we had little buttons that had the square root button on there, everybody can punch, take 24, hit the radical square root button on it, and come up with a digital answer. The book does not want you to do that. They want you to break these apart and find perfect squares. So think of perfect squares of 4, 9, 16, 25, 36. Okay, so think of perfect squares. So 4 times 6 is 24, and the reason I chose that, here's a perfect square root of 4 is 2. So when you evaluate it, yeah, that's how you simplify, and a square root of 6 you leave alone because it's excuse me, getting tongue-tied. It's not a perfect square, so you leave it in that format. Okay, that's more precise than going to the calculator and getting a digital number. Because that digital number is because the square root of 6, by the way, class, here I'm getting on a tangent, that's an irrational number. Okay, it's not a number that you could put in the form of a over b, which is a rational number. That number goes on forever and ever. There's no exact number multiplied by itself that will give you the square root of 6. However, 4 there is. 2 times 2 is 4. Okay, so let's work on these. Square root of 108. Now these get a little crazy here. They take a little bit of work here. Again, you want to think of, I'm going to give you guys a table here. It's going to help you out here. I'm going to send it to you. I usually hand it out in class here. Perfect square tables and cube root tables, they'll help you out here. So 108, think of factors of it. You realize that 36 times 3 is 108, and I chose that because the square root of 36 is 6. There's a perfect square. You want to pull that out. You're left with the square root of 3. Okay. One of the ways to do these is start taking 108 and divide it by 2, divide it by 3, divide it by 4, and see what the other product is. And if you see a perfect square, then you'll be on your way. Okay, that's how I like to do those. Look at number D here, the cube root of 16. You've got to think of cube root of 8 is 2. So 8 times 2 is 16, so I'm going to pull that perfect cube root out. and I'm going to replace it with the 2, and you leave the cube root of 2 alone. Okay, so that is the simplified form that they were looking for. Okay, so we're kind of cruising here. Example 5 is going to give us some more answers here. Let's just kind of leave it like this so I don't get too confusing here. Okay, square root of 16 m to the third. We now got some variables. We're going to apply what we learned up here. You get the square root. Now you know that index is 2, so don't forget that. Square root of 16, you break them apart. You're allowed to use multiplication and break apart the factors. Square root of 16 is going to be 4. Now I have a suggestion for everybody right now. Break these apart first. Keep the radical signs. Don't execute the radicals until you're ready to do it and you are ready to write those results. Okay. A lot of students will take answers like this. Take the square root of 16, write 4, leave the radical sign, and then write 2. You see why that's wrong? Because you double radicaled it. Okay. So m to the third, the exponent is greater than the index number. There's a 2 there. So you break it apart, go down to the next even number, so m squared times m to the first, because you're adding. 2 plus 1 is 3. The square root of m squared is m. Square root of 16 is 4, and the square root of m you leave. Okay, that's how you work those guys. Look at example B here. Square root of 200 times the square root of k to the 7th times the square root of q to the 8th. Break them down. 200 can be broken down in the square root of 100 times the square root of 2. Why did I do that? Because the square root of 100 is 10. So I broke that apart. Square root of 2 is going to stay that way. K to the 6th. Okay. Now, a couple ways to do this. Here's the short. I'm going to give you the shortcut. Whenever, I picked the 6th because I want k to the 6th times k to the 1st. Add the exponents, give you the 7. Okay, you've got the radical signs there. Now, whenever you're taking the square root and the exponent is even, the shortcut is to drop the radical and cut the exponent in half. So 6 becomes 3. And there's your answer. Now, let me come over here real quick. K to the 6th, the square root. Okay, now if I put the 2 up there, you could have k, write it as an exponent, 6 divided by 2. Remember, you're using your right-hand L rule. 6 divided by 2 equals 3. Another way to look at those, let me come up here, running out of room, is k to the 6th could be replaced with k, put the squared like this, because the square root undoes the squaring, so it all goes away. What do you need to put inside the inside exponent? K to the what times 2 equals 6. The answer 3, and therefore square root undoes squaring, and the base drops down, and there's k to the 3rd. Okay, hopefully that helps out. So you got a couple ways to look at it. I just recommend q to the square root of q to the 8th. You know it's an even exponent. Cut it in half, drop the radical, and you got your answer of q to the 4th. Okay, so just clean this up after here. Here's your 10. Square root of 2 and the square root of k were combined underneath the radical. Q to the 4th came down, q to the 3rd came down, and you got your answer. Okay, so hopefully that helps everybody. Here's another explanation of q to the 8th, why the answer is q to the 4th. You could see I chose this way was to, the index is 2, the exponent, I want to force it to 2 because I know they will cancel each other out. Q to the what gives you 8, and the answer is 4. 4 times 2 is 8. Therefore, there's your final answer, q to the 4th. Okay, hopefully everybody likes that little shortcut there. It makes life easy. Example C. Now, here's something really important. We work with square root mode so much that whenever you see the index is 3, you've got to do a warning, I'm in cube root mode. You got to train your brain to say you're in cube roots. Okay, so you're going to take the cube roots. What I did over here was I reorganized everything that could take the perfect cube root of. So I took out the -8. Can you take the cube root of -8? The answer is yes, -2. Can you take x to the 4th? I replaced with x to the 3rd, x to the 1st. 3 plus 1 is 4. Y to the 5 was 3 plus 2. Why did I pick the 3? Because cube root undoes cubing, so you come up with x and y here. When you execute the radical, over here you're still left with the cube root of x times y squared. And so you just bring that down. X, y squared, cube root. Okay, there you go. It's a good warm up there. We're cruising along here with simplifying radicals here. So Mr. McHugh going to check off here now. I will see you for the last page of 8.3, and we're going to go. I see Pythagorean theorem coming up down the road. So I'll see you then. Okay, bye.